A wise man once told me, if you're not part of the solution, you're part of the precipitate.
Boo! Boo!
That's right, today we're talking about solutions and solubility. Hit the theme.
Ain't nothing but a chem thing, baby. Two flipped out teachers going crazy. Lancaster is a district that pays me. Unbreakable, so please don't try to break this. But back to the lecture at hand.
Hello and welcome to another episode of SchuFu coming at you. I'm your host Fu, and with me as always is Shu.
Shu know it.
So Shu, starting a brand new unit on aqueous solutions.
Yeah, a lot of what we're going to talk about in this first lesson may sound familiar to you, but we're going to dive a little bit deeper. So let's get started. Solutions and solubility, a lesson from the Solutions unit. Introduction. A solution is a homogeneous mixture. Remember, homogeneous means an even distribution of matter, and mixture is the physical combination of two or more substances. So a solution has two substances physically combined, but the particles are distributed evenly. Usually that means we can see through a solution. Examples include salt water, water and ethanol, air, or a bronze alloy. Now the alloy you can't see through, but if you recall from earlier in the year, we talked about how you could take two metals, melt them down, mix them evenly, and then when it cools back down to a solid, it's still homogeneous. Non-examples include sand and water, oil and water, or copper and zinc pellets. These would be heterogeneous mixtures because the particles are unevenly distributed. We'll be focusing on aqueous solutions in this unit.
All right, ladies and gentlemen, get your 3D glasses out. Now, I forgot mine at home, but luckily I have Shu's prescription glasses, and these are in 3D. So here we're going to show an animation of salt dissolving in water. All right, so as you can see, we have a crystal lattice of salt. This is table salt, NaCl. Now it's got a crystal lattice because it's got those alternating positive and negative ions again. Now the green ions are chloride ions, they're negatively charged. And when the water molecule interacts with it, the positive side, or the hydrogen side of water, is going to surround that negative chloride ion. Now likewise with a sodium ion being positively charged, the negative side, or the oxygen side of water, is going to surround that ion, and eventually if you have enough water molecules around that ion, it's going to pull them apart. Whoa, look out, you got your 3D glasses on, this is kind of crazy. All right, so as this process continues, we call this a molecule ion attraction. So if you recall from bonding and intermolecular forces, this is one of those forces at play here. Now, as this process continues, eventually all of the salt will be dissolved in the water. Solute, solvente, solutione, dissolve. A solute is the substance that is dissolved in the solvent. It's present in the smaller mole amount. A solvent is the substance that the solute dissolves in. It's present in the larger mole amount. For an aqueous solution, the solvent is always water. Solute plus solvent always yields a solution. This is a physical change because dissolving is just occurring. This may be an endothermic or exothermic process.
Pretty blue crystals in 3D. I just love CuSO4-5H2O.
Dissolved in water. All I've got to do is take the blue crystals, add it to water, stir it up, and I've got a solution. Now when I do that, it actually feels slightly cold to the touch. Now, why would it be cold to the touch? It must be an endothermic process. Heat is being absorbed by the solution from the surroundings, and that's why it feels cold to me. Concentrated versus dilute solutions. A concentrated solution has a relatively large amount of solute, whereas a dilute solution has a relatively small amount of solute. These are qualitative terms, not quantitative terms. A concentrated solution still has more solvent than solute. For colored solutions, a more concentrated solution simply has a darker color.
So Shu, we have these 5 flasks in front of us here, and I got a couple questions for you. Okay, so of these 5, we have 5 solutions inside these flasks. Which one do you think is the most concentrated?
Most concentrated would be this one, I think.
All right, so why do you say that?
Well, it's the darkest, so to me, that means that there must be a lot of solute dissolved in the water, and that's why it's so dark.
Good, good. That's a good observation there. So what about which one is the most dilute?
Most dilute then would have to be that one.
Okay. Why do you say that?
Well, it's the lightest, so if it's the lightest, it would have a lower amount of solute dissolved in the water.
Okay, good, good. All right, one final question for you. All right, let's take a look at this middle one here.
Okay.
Okay, what would you say? Is that concentrated or is that dilute?
Not sure. I mean, it's kind of right in the middle, so, I mean, the middle one's darker than this one, so the middle one would be more concentrated than this.
Okay.
But it's lighter than this one, so it'd actually be more dilute in the middle than this one over here.
All right, so notice what you did to arrive at both those observations. You had to look at two flasks.
Okay.
Right? So we don't have numbers when we're talking about concentrated versus dilute. This is a very qualitative observation. It's
Okay.
not quantitative. So when you were looking at this one to determine whether it was concentrated or dilute, you had to look at another flask to compare it. So a good thing to keep in mind here is to always have some other solution to compare it to when thinking about concentrated or dilute.
Okay. You try number 1. What are 2 ways that a solution could be made more concentrated? You try number 2. What is 1 way that a solution could be made more dilute?
Solubility. Solubility is the degree to which a solute dissolves in a solvent. If a solute is soluble, then a large quantity can be dissolved. If a solute is insoluble, then very little can be dissolved.
Table F solubility guidelines for aqueous solutions should look familiar to you. We've used it before when we were predicting products of double replacement reactions. In those reactions, we created products that we wanted to see if they formed a precipitate or not, a solid in that reaction solution. Now, in this context, we're simply trying to figure out if something dissolves or doesn't dissolve in water. So if you have a soluble compound, that means it will dissolve and it will be aqueous. And if you get from table F that we have an insoluble compound, that means that it won't dissolve and it remains a solid.
You try number 3. Which salt, now salts are ionic compounds, is most soluble in water? Now you're going to use table F to determine which one of these are soluble or insoluble, and you should look up all 4 of them to determine which one is most soluble. And then please explain how you know this.
Saturation. Even a soluble substance cannot dissolve without limitation. The degree of saturation quantifies how much solute can be dissolved. Saturation depends on 3 things: the identity of the solute, the mass of solvent, which is water present, and the temperature of the solution.
Unsaturated solutions. In an unsaturated solution, more solute can be dissolved in a given amount of solvent at the given temperature. If more solute is added, dissolving occurs. Looks clear in appearance. So to further illustrate this concept of an unsaturated solution, we're going to use an analogy here. We're going to talk about a sponge, and I think most people have used a sponge. So an unsaturated sponge would be a sponge that can hold more water. So this sponge might look dry, it might look damp, it might even look pretty wet, but you know it's unsaturated because the sponge can hold more water.
Saturated solutions. In a saturated solution, the maximum amount of solute is dissolved in the given amount of solvent at the given temperature. If more solute is added, wait for it, it won't dissolve, but sink to the bottom instead. Solid is always present in a saturated solution.
Solid is always present in a saturated solution!
Dissolving and crystallizing are occurring on a molecular level. This is an equilibrium, even though you see no change. If we take a look at the picture to the right, you see that we have CaF2 solids sitting at the bottom of the beaker, and we have ions, Ca+2 and F- that are moving around in the solution. Now there's a double arrow between the solid and solution, and that double arrow represents that we have an equilibrium, a state of balance between the ions and the solid. That means we have dissolving occurring, the solid is turning into ions, but we also have precipitation or crystallization occurring with the ions going back to solid. And that's why
solid is always present in a saturated solution! All All right, so to further our analogy with a sponge here, when we talk about saturated solutions, right? Saturated solutions are holding the maximum amount. So a sponge that's saturated is holding the maximum amount of water that that sponge can hold. So you would know this because if you tried to get more water into the sponge, more water would just fall out the bottom. It's holding all it can. That's a saturated sponge.
Good one.
Supersaturated solutions. In a supersaturated solution, more than the maximum amount of solute is dissolved in the given amount of solvent at the given temperature. This is accomplished by heating up a saturated solution and adding more solute. After cooling, the extra solute stays dissolved, but the solution is very unstable. If more solute is added, the excess solute crystallizes back out of the solution. This is actually how rock candy is made.
We're going to take a look at a new reference table today, Table G's solubility curves. Table G shows how the solubility in grams of solute per 100 grams of water varies with temperature. Let's take a look. On the x-axis, we have temperature in degrees Celsius, and on the y, we have solubility. It's the grams of solute dissolved in, and this is key, 100 grams of water. That can actually change, but more on that later. Notice how for most substances, solubility increases with increasing temperature. That's a positive slope. So for example, if we look at something like KNO3, as temperature increases from left to right, we see that it slopes upward. That means that the solubility is increasing. In other words, we can fit more grams of KNO3 in 100 grams of water at that higher temperature. These substances are solid ionic salts. Notice how for some substances, solubility decreases with increasing temperature. That would be a negative slope. So if we take a look at something like HCl, HCl has a downward sloping curve. That means as temperature is increasing across the x-axis, that the solubility is actually going down. We fit fewer grams of solute in 100 grams of water. These substances are gaseous molecular compounds.
If a given amount of solute dissolves in 100 grams of water falls on the line, the solution is saturated. So taking a look at table G, we're going to take a look at NaCl, and that's right down here. If we have 40 grams of solute, NaCl, that's right here, grams of solutes on my y-axis, is dissolved in it, we're going to say 90 degrees is our temperature too, down here on the x-axis. Well, if I follow those two lines, I get this point right here, and that point is right on the line for NaCl. That means that we can't put any more NaCl. That line is the max. So if you remember, that's the definition of a saturated solution. So it's right on the line, it's saturated. If a given amount of solute dissolved in 100 grams of water falls below the line, the solution is unsaturated. So we're going to take the same temperature at 90, but in this case, we're going to go with 30 grams of NaCl. So 30 is less than that 40, so naturally we see that the dot is below that line. And since it's below that line, this is considered unsaturated because it can hold more. We could actually put 10 more grams in this solution to get it to saturated. So since it can hold more, it's unsaturated. If a given amount of solute dissolved in 100 grams of water falls above the line, the solution is supersaturated. So in this case, same solution, same temperature, but we're going to say 50 grams this time. Now 50 at 90 degrees Celsius falls above the line for NaCl. And since it's above the line, it's holding too much. It's holding more than it should. And this is what supersaturated means. All right, we have an example problem here for you. Shu, are you ready?
I'm ready.
All right, we're going to use table G, the solubility curves at standard pressure. If 65 grams of NaNO3 are added to 100 grams of H2O at 10 degrees Celsius, what type of solution is formed? All right, Shu, so we've got some numbers here, but let's first figure out what substance we're dealing with.
All right, well, the solute is NaNO3.
Good, so let's find that on table G.
All right, NaNO3 is right there.
Perfect. All right, so now we can start to pick out some numbers that will correspond to our X and Y axis.
Well, let's start with the x-axis. I've got 10 degrees Celsius,
Okay,
which is right here.
perfect.
I'll go with the 65 grams. That should be on the y-axis, which would be out there.
Okay, now we also have the number 100 for grams of water in our problem. Now, it's important that they say that because table G, if you recall, is based on how much dissolves in 100 grams of water. So this is just confirming that for us.
Okay, so that's what we see labeled per 100 grams of water on the y-axis.
Perfect.
All right, so I guess I should find my point then.
Good, so let's find that point where the X and Y numbers cross.
So I should be right about there.
Okay, so now we want to take this point and we want to see in reference to the substance we're talking about, where is it? Is it on the line, is it below the line, or is it above the line?
All right, well, just to kind of make it clear, we're looking at this line right here. And so it looks like we are below it.
Good, we are below it. So what type of solution do we have if we're below the line?
So if we're below it, it means we'd be able to dissolve more, so we must be an unsaturated solution.
That would be correct. All right, so while you're writing that down, there's one thing I'd like to point out here about table G, and this is something that students can get confused on. We circled sodium nitrate, NaNO3. Right next to that is KNO3.
Okay.
Now they're both nitrates, they both end with NO3, so students often get these confused because they're so close, plus they cross each other, so you gotta be careful which one you're dealing with. So if you accidentally thought this was KNO3 looking at that line, you would have got a wrong answer. So please, when you're using table G, be careful as to what line you're looking at because these all kind of crisscross.
Sounds good.
You try number 4. If 90 grams of KNO3 are dissolved in 100 grams of H2O at 40 degrees Celsius, what type of solution is formed? Use table G to figure out if this is a saturated, unsaturated, or supersaturated solution.
Also, don't ignore the mass of water given in the problem, as it's not always 100 grams. If the grams of water are less than 100 grams, then it will take a proportionally lower amount of solute to saturate the solution. If the grams of water are more than 100 grams, then it will take a proportionally higher amount of solute to saturate the solution. All right, we're gonna do another table G example. Are you ready, Fu?
I am.
Okay, how many grams of NaNO3 must be added to 200 grams of H2O to form a saturated solution at 20 degrees Celsius? All right, let's begin with what is our solute in this problem?
All right, well, it says how many grams of NaNO3, so that is my solute.
All right, let's find that line on table G.
Okay, NaNO3 is right up here.
All right, let's take a look at some of the numbers. Now we're gonna find in this problem the number of grams of NaNO3, but what else do they give us number-wise?
All right, well, when doing these problems, I love to find the temperature first, kind of get that out of the way, and I see I'm at 20 degrees Celsius.
All right, let's find that on the x-axis there.
It's right down there.
All right, now what other numbers do they give us?
The only other number I see is this 200, but that says grams of water.
Yeah, that looks a little different than we've seen it before. How many grams of water are we normally given in the problem?
And we're usually at 100.
We're usually at 100, and again, if you take a look at the y-axis, why don't you circle that we're always out of 100 grams of water, and yet this question is asking us about 200 grams of water. So any thoughts as to what we might have to do?
Well, 200 grams of water is twice as much as the 100 grams on table G, so I'm guessing I gotta double it,
You're gonna have to double it.
right? This is kind of like making Kool-Aid for my party, right?
Yeah.
If I make Kool-Aid the same way, but I double the water but don't double the sugar, it's gonna taste like crap.
Indeed it will.
I gotta double that sugar. All right, so I'm gonna double it at the end.
All right, so we've got to read table G as it stands out of 100, so let's do that first.
Okay, so at 20 degrees, I follow that line up for NaNO3 and I get right there.
And just to reiterate, we're going right to the line because they're talking about a saturated solution.
Okay.
And what do we get for a value there?
Looks like it's about 88 grams.
88 grams looks good. Now that's 88 grams out of 100 grams of water. And we want to find the number of grams to saturate 200 grams of water.
Okay.
It's proportional.
All right, so I'm just going to use 200 grams. And I know this is a pretty easy math problem to set up and even do in my head, but just to show the math here, let's get this one out of here. So double 88 is
Double 88.
176.
176. That would be the number of grams of any NO3 needed to saturate 200 grams of water. Nice job.
Okay.
You try number 5. How many grams of KNO3 are needed to saturate 50 grams of H2O at 50 degrees Celsius? Use Table G to determine your answer, and notice that the grams of water are not 100 grams.
Well, that's going to do it for today's episode on Solutions and Solubility.
It's been emotional.
Today's episode is brought to you by
Bathe and Brew Shower Coffee Maker and Soap Dispenser. Cut your morning routine in half. Stainless housing stands up to even the harshest dandruff shampoos. Use its standard 120 volt outlet. Finally, you can take cream with your conditioner.
Brews 1 cup per 12 gallons of water.
But we never off, always on till the break of dawn. SCIENCE in the hall they call S-Wing. You know we never wear a tie. Like my homies, boys to men, it's so hard to say goodbye.
Like this, that, and this, and it's like that, and like this, and like that, and it's like this.
You're going in low power mode.
Plug and chill to the next episode.